discussing about the optimum quantizers, and also we talked about the nonlinear quantizer in the form of the mu law. Now, what essentially we had seen is that the non-uniform quantizer was less sensitive to the variance of the signal. To some extent it was, but for a relatively flat zone, we had seen that the signal to noise ratio was more or less constant. So that means to say that it was independent more or less on the sigma x parameter, that's to say the variance of the signal. Of course, although it was uniform, although the SNR was uniform, that's what we had shown in some of the example graphs. Okay, I mean, it was also seen that the SNR value, that the overall SNR value was much lower as compared to what it would have been if we had used the uniform quantizer. Okay, but beyond a certain stage, we found that the performance of the mu law was better than the uniform quantizer, especially wherever we are having the ratio of sigma x by x max, okay, to be on the higher side. Okay, that's I mean, these details we had seen in the last class, and then we had also put forward the theory behind the optimal quantizers, and there what we had said is that the quantizer parameters, that means to say the decision levels and the reconstruction levels, these are to be designed in accordance with the signal variance. Okay, but in the process we had also seen that I mean, especially for the speech, where we have got a very large variations in amplitude, okay, even for one particular speaker, okay, under the different conditions of communication, one can have different amplitude levels, and that gives rise to a very large dynamic range of the values which the speech signal can attain. Okay, and another characteristic of the speech signal is that it is not a stationary process, so it varies from frame to frame. And another matter of concern is that we have got speech versus silence. So considering all these considerations, okay, we had argued towards the end of the last class that it is not the right kind of solution to use the optimum quantizer, although optimum quantizer when matched to the signal variance would give us a much better SNR as compared to the mu law. But mu law, I mean, usage of mu law is preferred for the speech signals under different conditions. Now today we are going to study that in order to make the quantizer getting itself adapted to the variance in the signal, okay, there is yet another strategy. That's what we are going to discuss, and today's topic of discussion is going to be what is called as the adaptive quantization. So as the name implies, okay, an adaptive quantizer would mean those kind of quantizers where the quantization parameters, okay, would be dynamically adjusted, okay, in accordance with the signal variance. Means its parameters should match according to the variation in the signal. So now what are the parameters that we can change? Now one of that is of course the step size, that is the delta. Now so long we were assuming that the delta was a constant quantity. I mean, when we take the uniform quantizer, it was absolutely equal for all the different levels. We were having a having equal step size. Okay, but in the case of the non-uniform, although the step sizes are unequal, so essentially we have got delta 1, delta 2, etc. okay, for the different levels, but in such case also all those different step sizes that we consider, those were also constant for a particular design of the quantizer. Means if we consider any particular value of mu in the mu law quantizer, in that case the step sizes are essentially pre-designed. Okay. But in the case of adaptive quantization, the step sizes will be made to vary in accordance with the signal. So what would you expect? If the signal variance increases, if sigma x happens to increase, in that case what should we logically do to the value of the delta, the step size? Increase or decrease? Yes, if sigma x increases, we should also increase delta, because essentially in the process of quantization now we can do some form of over quantization is possible, because the signal level is up, okay, the variance of the signal is higher, so we can use larger value of delta. And on the other hand, we can I mean when we have the signal variance as smaller, in that case we are going to have the delta value also as smaller. Okay. So essentially what we want is that with such a variation in the signal amplitude of the speech signal, okay, it should be changing, this delta should be changing from time to time. So now delta we are not assuming as a constant delta, rather we are going to say that this delta would be parameterized by n, okay, where n is going to be a parameter corresponding to the sequence. Now delta, instead of writing delta, we are going to write delta as a function of n. Now whether we will be sampling this new delta for every samples, or whether we are going to sample it at a much lower frequency as compared to the sequence, I mean that means to say that the rate at which the sampling is performed, these aspects we are going to discuss in course of time, okay. But essentially it will not be the delta anymore, the fixed delta anymore, but it will be the delta as a parameter of n. Now this is one way of achieving the adaptive quantization, okay. Yet another methodology to have an adaptive quantizer is that before you take the, I mean before you perform the quantization, okay, you multiply the signal by some gain, okay. You just introduce a gain corresponding to the signal, and that gain is something which is not a constant gain, but that gain will change according to the variance of the signal. So what we want is that we will not be actually quantizing the original signal x of n, but instead we will be quantizing y of n, where y of n will be given by x of n multiplied by a gain parameter g, which also will be dependent upon n. So this g will be a time varying gain. So this will be a time varying gain. Like the way delta n is essentially a time varying step size or an adaptive step size, Gn is going to be a time varying gain. So that will be a second approach, in which case before quantizing the signal we will be multiplying it by the time varying gain. So we get y of n, okay, and it is the y of n which we will be quantizing, okay, and then encoding, okay. So at the decoder end, what we have to do? We have to do the reverse process. That means to say that when we recover y cap of n at the decoder, there we have to divide it by g of n so as to get back the x cap of n, right. So we will see the blocks of these two adaptive quantization schemes. Now what I said is that this delta n should be proportional to the signal variance, right. Now what should this gain be? Should it be proportional to the signal variance, directly proportional to the signal variance? It should be inversely proportional to the signal variance. Why? Because as the signal variance changes, this xn, that changes, okay, and we have to compensate. So we have to compensate for this increase. by reducing g of n. So, g of n should have the variance in its reciprocal. Okay. So, as a result of that, what we will try to do is that this product xn and gn, that should be maintained as uniform as as independent as possible with sigma x. That is the basic idea, that it should adapt itself to the variance of the signal, right. So, we will see in a block diagram form that how these two quantizers, okay, how these two adaptive quantization schemes would look like. So, when we have the variable step size representation, so this is the scheme 1, okay, which is the variable step size representation. So, in this case, as we said, that x of n is the input. So, x of n will be passed through the quantizer, which I am denoting by this block q. So, at the output of the quantizer, we are going to write it as x cap of n, which is the quantized signal, and then this will be encoded. So, we will put an encoder, and after that we will be having the actual encoded sequence which will be formed. So, encoded sequence will be denoted by C of n. So, C of n is the encoded sequence, and this quantizer as well as the encoder, this will be controlled by the step size. So, the step size will now be written as delta n, as I said. Okay. So, this will be on the encoder side, and on the decoder side, okay, we should be receiving ideally the same Cn. Okay. But you know that in between this encoder and the decoder, we are going to have the communication channel. So, the communication channel may introduce, okay, some amount of noise. So, we cannot all the time assume that, although in many of the analysis we simply make an ideal assumption that the channel is a lossless channel, but practical channels we know are not lossless. So, if we have to write it in a proper way, we should not be writing it as Cn, but we should be writing it as C prime n, okay, where C prime n will be equal to Cn only under the ideal lossless channel situations. Okay. So, this C prime n will pass through the reverse block of this, that means to say that it will go through the decoder, okay, and the output of the decoder will be y prime cap n, okay, and no, not y, in this case we are dealing with x only. So, this we will call as x prime n, okay, and this decoder, its parameter will be controlled by delta n, isn't it? But just look at one thing, that in this case delta is a time varying quantity. Okay. Now, in the earlier case where delta was fixed, okay, then delta is well known to the encoder and the decoder beforehand, because you are going to use a particular quantization scheme, either a uniform quantization scheme or a non-uniform quantization scheme with a particular value of mu. So, everything, all the step sizes are known beforehand to the encoder and decoder. So, there was no need to transmit that information in the channel. But whereas in this case, because delta is varying with n, okay, we have to update the decoder with whatever value of delta the encoder is using. So, that is why this value of delta n also should be sent into the channel. I mean, it should also be encoded and sent to the channel. So, we will be sending delta n, and here ideally we should be receiving at the decoder end delta n only, but again considering the non-ideal situations of the channel, let us not write it as delta n, let us write it as delta prime n. Okay. So, ideally for this we should have C prime n is equal to Cn for lossless, delta prime n should be equal to delta n, and in that case only we can expect to get that x cap prime of n is going to be x cap of n. We certainly cannot get x of n exactly because there is already a quantization process which is there, but x prime of n can be made equal to x cap of n, okay, if the channel happens to be noiseless. Now, what we have represented about this delta n is okay as a scheme, but we have to definitely study that how will this delta n be decided, because we said that this delta n, because of this dependence upon n, it is going to be adaptive. So, it must somehow know that how the signal variance is changing. So, it should monitor the signal. Okay. So, how it monitors the signal, that aspect we will come shortly. So, this is about the scheme 1, okay, and let us have a look at the scheme 2, where instead of providing a time varying step size, we are going to provide a time varying gain. So, the scheme 2 would look like this. So, this is the variable gain representation. So, in this case the input is xn and we have a block where a multiplication will be performed, and this multiplication will be by g of n. Okay, just look at this part, that we are saying yn is xn into gn. So, this is xn and gn is the time varying gain. How we derive it, that we will see, and the output of this will be the product of xn gn, which we are calling as yn. So, now instead of quantizing xn, which we did in the case of the variable step size where xn was directly quantized, in this case yn will be quantized. So, this yn will be put through the quantizer, the q block, and the output of this will be y cap of n, the quantized y, and then we will pass it through the encoder. Okay. The encoder generates the encoded sequence Cn. Now, in this case the quantizer and the encoder should be controlled by the quantization parameter delta. Okay. But in this case delta is fixed. So, we need not have to transmit the delta, okay, into the channel, and C of n goes into the channel and C of n gets decoded. I mean, at the input of the decoder we will call it as C prime n as before, and then it goes to the decoder. So, the decoder output we are going to write as y prime cap n, okay, because it is the y cap of n which we are going to recover, exactly y cap n if the channel is lossless, but otherwise it will be in general y cap n, and this y cap n will be put through a divider block, okay, where this y prime cap n will be divided by the gain g of n, the time varying gain g of n, and we should be getting x prime n cap. Okay. This is what we can expect to get. So, x n here, x prime cap n over here. Okay. Now, this time varying gain what we are showing over here, this time varying gain must be known to the decoder also. The encoder is using the time varying gain to multiply x of n. So, likewise the decoder should know the same g of n, okay, in order to divide y prime cap of n. So, this g of n information should be sent into the channel. So, here we must send g of n, and here we will be receiving what we will write as G prime n. Okay. So, it will be y prime cap n divided by G prime n, which gives rise to x prime cap n. Okay. So, this is going to be the reconstructed or the decoded signal. So, under the noiseless channel case, x prime cap n is going to be x prime n. Now, we do not have any x prime n directly in this block diagram, because we are not quantizing x n, rather we are quantizing y of n, but x prime n will be the equivalent quantized representation of the signal x of n. Okay. So, in this case, what we have to do is to transmit both Cn and Gn. In the earlier case, we were transmitting Cn and delta n, but in variable gain representation, this Cn and Gn, that is what we have to send. Now, we will treat both these schemes simultaneously, because in whatever methodology we can extract the time varying properties of the signal, okay, we can use it either to control the adaptive step size or to control the adaptive gain. I mean, in principle both are going to be the same. So, that is why we are treating them simultaneously. Now, one of the aspects that we can think over, that look at scheme 1, okay, or look at scheme 2, okay, what are we going to, I mean, what is our requirement? We must formulate this delta n properly, that depending upon the signal. So, we have to monitor the signal, okay, and based on that we must decide that what should be the value of this delta n. Now, where we can monitor the signal, okay. Now, we have got, if you look at the block diagram over here, this is the input part of the signal, and this Cn is also carrying the signal, but only thing is that Cn is the coded form of the signal, right. So, we can either derive the parameters delta n, okay, by I mean from the original signal x of n, okay, or we can derive delta n by looking at the encoded sequence C of n. In case we are estimating delta n from xn directly, in that case we must have a block which computes the adaptive step size in the forward loop, okay. Whereas, if we are going to compute delta n by looking at Cn, that is to say the encoded sequence, in that case we must have an adaptive quantizer computation loop which will be in the feedback path of the encoder. So, there are two schemes, okay. There are two methodologies for achieving adaptive quantization, and one of the methodology is to use a feed forward adaptation, and the second is what is called as the feedback adaptation. So, adaptive quantization, we can say that from the adaptation point of view, one can have either a feed forward adaptation or it could be a feedback adaptation. And the feed forward or the feedback, this methodology should be possible for both variable step size as well as for variable gain, okay. Because if we take the feed forward mechanism could be used for both. So, let us see the step size adaptation. So, let us first discuss the feed forward adaptation. So, in feed forward adaptation, what we need to do is that the block diagram, I mean, if we have understood the earlier block diagram, which is a general block diagram where we did not talk about how the adaptation is going to take place, but in this case specifically for a feed forward adaptation. So, this is going to be the feed forward adaptation. Xn goes through Q, output is X cap n, and that goes to the encoder. This goes to Cn. Up to this we do not have any change. Only thing is that here we are going to have delta n. That also we had seen in the variable step size representation, but the only new addition will be that this delta n will be decided by a block which will be in the feed forward, which basically we say that which is a step size adaptation system. Now, what is this adaptation system? Definitely we understand it by now that the step size adaptation system is going to compute the variance of the signal, right. So, it is the variance signal computation which is going to take place in this block diagram, that also we can say very definitely. So, this block comes in the feed forward loop, and this delta n, even in this scheme also we need to transmit delta n as before, right. So, the encoder, feed forward adaptation encoder will carry both Cn and delta n into the channel, and correspondingly at the decoder there is no change. Decoder will be getting C prime n, and there will be a decoder block over here, and then we are going to have delta prime n, and then the output of this will be X prime cap of n. So, this is the overall feed forward adaptation scheme, okay. And this is for the step size adaptation, and if we see the gain adaptation system, okay, that also will look somewhat similar. So, what we need to do is that for the gain adaptation, X of n will be here, and here we have the multiplier, and this is the yn. Then we are going to have Q y cap n at the output, the encoder, and output of the encoder is C of n, and the quantizer and the encoder has got the parameter delta, which in this case is a constant parameter delta. That is what we are going to have. And now what we have to do is to derive this Gn from Xn. Again we are going to adopt the same feed forward mechanism. So, in the feed forward mechanism we will feed this Xn, the input directly, and then that goes through what is called as the gain adaptation system, and the gain adaptation system block that goes to the Gn, okay, and this Gn needs to be transmitted, right. So, Gn also should be going from the output of the encoder. So, this will be the encoder overall block diagram, and the decoder will be this C prime n will be received. It goes through the decoder, and as before we are going to have y prime cap of n, and there will be a divider block, and it will be divided by, instead of Gn we write G prime n, and this will be X prime cap n, which will be essentially y prime cap n divided by G prime of n. So, this is the feed forward adaptation only, but based on the gain adaptation. Earlier was the step size adaptation, in this case it is the gain adaptation. So now what we have to do is to know about this step size adaptation or this gain adaptation, that how exactly we do it. Now as we said that one has to estimate the signal's variance. Okay. Now the variance, what we have seen is that one of the approaches is that we can estimate the variance by looking at the short time energy. Okay. The signal is a zero mean signal, that is what we are assuming. So the short time energy what we are having is giving us a measure of the variance. And how we are going to express that? Okay. The short time energy, we are going to write it as sigma square n, which will be the summation of x square m, okay, into the filter function, the low pass filter function h of n minus m, and we are going to sum it up for m is equal to minus infinity to plus infinity. This is an infinite summation, but the truncation will be definitely obtained by this h of n minus m function, which is typically an FIR filter, or even if it is an IIR filter, okay, it should be a realizable IIR filter. Okay. Now one of the simple examples that we can take for this is that we can take h of n to be alpha to the power n minus 1, okay, for n greater than or equal to 1, and this we can say that is 0 otherwise. That means to say that for n equal to 0 or any negative values of n, okay, I mean rather n less than unity, we are going to have the value of hn to be equal to 0. This function we had seen in earlier examples also, we were considering these functions. So now for stability, of course, we are going to have the parameter alpha lying between 0 and 1, right. So using this, we can write down the sigma square n as the summation m is equal to minus infinity to plus infinity summation x square m alpha to the power n minus m minus 1, right. And this we can also write down in the form of a difference equation. So in the form of difference equation, we can write it as sigma square n is equal to alpha into sigma square n minus 1 plus x square n minus 1. So this is going to be quite a useful expression for us, okay, that we know the earlier estimate, the previous estimate of the signal variance, okay, multiplied by this parameter alpha, okay, and then we are going to add up this x square n minus 1 term. That means to say the new sample we are adding, and that gives us the new estimate of sigma square n. So it could be used, I mean this is a recursive way of computing sigma square n. So if we get an updated estimate of the sigma square n, then accordingly we can vary the step size. In fact, the step size is made proportional to the standard deviation of the signal. So what we are going to write is that delta n will be equal to some constant delta 0 into sigma of n. Sigma of n is something which will be estimated given this equation. Okay. So this is about the time varying step size. Okay. This is the time varying step size, and the time varying gain will be similar. Only thing is that here it will not be multiplied by sigma n, but it will be divided by the standard deviation sigma n. So, time varying gain is given as g of n, which will be written as some constant gain g0 upon sigma n. Okay. So, now there are two issues, that is what we have to decide, that how would we, I mean how often are we going to change this sigma n? Okay. I mean, are we going to change it too fast, or are we going to change it too slow? I think that for short time signal analysis, for short time speech signal analysis, we have been encountering this question again and again, right? Now, I mean intuitively it obviously appears that if we go in for too much of short time in the computation of sigma n, okay, in that case, as the normal speech parameters vary, that means to say that with the harmonics that the vocal cord oscillations are giving, okay, that also will be picked up by the sigma n variations, and then accordingly we will be changing the step size for everything. And that means to say that although we want those variations to be there, but we will try to have some kind of an equalization effect. Okay. I mean we will try to give equal treatment to all, and even to the value of the sigma n at the non-speech sequence, that also will abruptly vary. Okay. On the other hand, we should not think of, see, after all, this sigma n, how we have derived? Sigma n we have derived through a process of low pass filtering. This h of n minus m, this is giving an effect of low pass filtering. So, definitely this low pass filter is going to have some upper cutoff frequency, and this upper cutoff frequency, so and because this upper cutoff frequency is there, there is no point in trying to have a sigma n, okay, which will be sampled, okay, at a rate which is considerably higher than that of the upper cutoff frequency of the low pass filter. Okay. So, in fact, I mean sigma n happens to be a much slower process, okay, as compared to the speech sampling. Speech sampling is going on at 8 kilohertz rate or 10 kilohertz rate, but that does not mean that sigma n will track accordingly. Just a very simple example, that if we take a speech waveform, something like this, a typical speech waveform, let us say, okay, that this is the amplitude, this axis we are plotting the amplitude of the speech signal, and this axis is, as it is, the time axis, right. So, we have something like this, that so, what we tried to show over here in this plot, that this part we can say is the voiced speech, right. This duration is the unvoiced speech. Again, this part happens to be the voiced. So, this is voiced, this is also voiced, and this is unvoiced. Now, this is how the signal amplitude is varying, or rather instead of signal amplitude we can talk about the signal energy also. Okay. Now, what happens is that the sigma n estimate, okay, sigma n estimate will not exactly track down according to this, it will not track down this variation, but the sigma n variation will be relatively slower. So, maybe that here we are having a situation something like this. So, this is how the sigma n varies. So, sigma n variation, you can see that it is a smooth process, right. So, it is a low pass filtered version. So, it is a smoother process. In fact, again look at the difference equation. The difference equation estimates this sigma n according to this. So, there is a parameter alpha which will be associated, right. Now, just qualitatively think that what will be the effect if alpha is high. High means, okay, for stability we have to make alpha restricted to 1, okay. Supposing it is very close to 1, say it is equal to 0.99, okay. That is one type of case, that is what we can say, and the other case is that where alpha we take to be much smaller, okay. Let us say that we take two situations, alpha is equal to 0.99 and another case we take where alpha is lower than that, alpha is 0.9. So, looking at the difference equation, how will these two values of alpha make a difference? You see, there are two terms in this sigma square n computation. One is alpha sigma square n minus 1 and the other is the addition with x square n minus 1. Now, if you make this quantity larger by having a larger value of alpha, means that you are inviting more contributions of this. That means to say that the past variance, past estimate of variance is going to have more effect on the present estimate of variance. So, which means to say that it does not allow us to make revised estimate of sigma n that fast. Whereas, if we make alpha smaller, in that case the contribution of this alpha sigma square n minus 1 term will be lower, okay. So, the signal variation which will be reflected by this x square n minus 1, that will influence the sigma square n more rapidly. So, now with lesser value of alpha, there will be more rapid variation to the signal variance, okay. Whereas, with higher value of alpha, the variation in sigma square n will be much smaller. So, as a result of that, in a typical situation, one would see that if we just think of a curve like this for the amplitude versus time, okay, and this is what we are plotting for x of n, right. Now, let us say that if we have a gain adaptive system, okay, if we follow the gain adaptation means that we are going to multiply this x of n by g of n, okay. So, if sigma n changes very rapidly, okay, sigma n changing very rapidly would obviously mean that this x of n gn, or rather the yn will have less sensitivity to the signal variance. So, as a result of that, this variation which you are having, okay, all these variations will be properly captured by this sigma n, okay, but it also takes care, I mean it will try to make more droops in between, okay. The revised sigma estimate, okay, may be something like this, that here a fall, and then here again because of this there is a rise, then there is a fall, then again there is a rise, then there is a fall, like this. So, the sigma's variation will not be a smoother variation, the sigma variation will be, I mean, much rapid, okay, as a result of that. And because of that, we will be having a more uniform. Now here the sigma n varies very much. So, here you see that sigma n falls, and sigma n falls more rapidly means that it will give rise to higher value of Gn. So, higher value of Gn means that these part will be more emphasized. So, when we see the Yn waveform, we will see that these parts will be boosted, and again these parts will not be boosted as much. So, as a result of that, the amplitude will try to have more amount of uniformity, I mean less dependence on variance, which is not always desirable, because it should actually capture the properties of the speech waveform. So, as a result of that, it is a good practice to have the sigma n, okay, to be as low frequency sampling as possible, okay, without of course disturbing the short time nature of the signal, because if we make it too much low pass filtered, I mean if the low pass filtering effect is highly pronounced, in that case the difficulty that we will be encountering is that from one frame to the other, the variation of that sigma n will not be that much. So, sigma n will be unable to track down the variation of the signal at all, okay, which is also not very desirable. Okay. So, definitely some amount of compromise, and another thing is that this Gn and sigma n, as we are seeing over here, that for speech waveforms, okay, this delta n and Gn, whatever adaptation we have, the step size adaptation or the gain adaptation, okay, it is going to be performed over a wide range, okay, but for practical implementation that range needs to be limited. So, when we talk about the gain, okay, the gain should be restricted within some practical bounds. So, we can say that it is restricted within G mean, the minimum gain, and G max, the maximum gain, and likewise the step size delta n should be restricted within delta max and delta mean, okay. And typically this ratio of these limits, it is seen that whether we call of G max by G mean, in all typical applications G max by G mean or the delta max by delta mean, okay, this is of the order of 100. 100 means that it contributes to an SNR of 40 dB. So, there could be a variation in gain in as much as 40 dB, and likewise there could be variation in the step size by as much as 40 dB. So, this is from the practical implementation consideration. So, we have seen that of course, this is the kind of adaptation that one should do, means the delta n and Gn that should be derived from the signal properties. Now, here we made use of the Xn directly in this equation, okay, that sigma square n is derived directly from x square m. Now, I mean it could also be derived in a feedback mechanism also, that is what I mentioned little earlier, and in that case it leads to the feedback adaptation system. Now, the feedback adaptation system I will be discussing in the next class. I will begin with the feedback adaptation system, and there we will see, we will notice one thing, that just look at this diagram where we are having a step size adaptation, or in this case the gain adaptation. We need to transmit Cn as well as Gn for gain adaptation, and for step size adaptation we need to transmit Cn and Gn. But supposing step size adaptation only we employ, and instead of having the step size adaptation through Xn, we have the step size adaptation through Cn, because Cn is also carrying the signal information. In that case, if the delta n information can be derived from Cn, in that case the encoder as well as the decoder can derive that information from Cn only. So, there will not be any need to transmit the information pertaining to delta n separately. So, that will be one of the advantages of the feedback adaptation mechanism, but all advantages are I mean every advantage is also associated with certain disadvantage. So, we will also see that what are the disadvantage of the feedback adaptation. In fact, I mean in a feedback adaptation, not only can step size adaptation leads to that the fact that only Cn will be sufficient, even for gain adaptation also, that if we have the gain adaptation from this Cn, then Cn itself should be a sufficient information. We did not have to send the Gn information into the channel. We can derive the Gn information from Cn itself at the decoder also. So, we will see that in the next class. Till then, thank you.